All right, so now let's say, what was it? So section 3.3, number 4, that's homework. That goes with yesterday's notes. And then the section 3.2, number 6, that's still extra credit. All right, so let's take a look. You want your note sheet out from yesterday, the one that I handed out yesterday. If you're not with us, then you got to go get that on eLearn or out of your folder. If you are with us and you don't have it, I can give you a note copy. Yes, right. It's definitely the one stated. And it should say, so you don't even really have to write this down. If you want to put this in your notebook, like, you know, C note sheet, you could do that. Otherwise, you could just use other notes for today. Optimization problem. And to optimize, you know, to either make it the most or the least, okay? We want to optimize, we want to get the most out of something, or in a few cases, that actually means to get the least out of something. Well, the most comes from a max, and the least comes from a min, which we've been talking about all chapter. All right, so let's take a look. Find two numbers whose sum is 24 and whose product is a maximum. So there's some restrictions here. There's two numbers and the sum has to be 24. So we'll just do two numbers. So this is example 1. X, are we okay? Sum means to add. So X plus Y has to equal 24. Find two numbers whose sum is 24. Okay. But their product, we want it as big as possible. So the product, X times Y, we want that answer as big as possible. Okay. So there's a lot of numbers out there that add up to be 24. Okay. So if we did, and you don't have to write this down, but like if we did 1 plus 23, okay, that gives us 24. What is the product? 1 times 23. You don't have to write this down. I just want you to kind of understand what we're doing here. So that gives us 23. Okay, what happens if it is 2 plus 22? That product, or that sum is 24, but 2 times 22 gives us 44, right? So we want two numbers, and they don't even have to be whole numbers, right? They could be fractions, decimals, things like that, just to kind of give you an idea of what we're trying to do here. Pick out two numbers that add to 24, but their product, when we multiply, is the biggest possible that it can be. Yeah, you can play with some of these. You might be able to just kind of like play around with, but eventually tomorrow, especially tomorrow, they're going to get a little bit harder. But should we do more? Do we kind of see where we're going at? Pick two numbers that add, but then we want the product to be as big as possible. All right, so to do it algebraically, this is the equation that we want the maximum. This is the equation where we want the max. So we want to substitute this information into here. I usually solve for y. I'm just so used to solving for y anyways. And so y equals 24 minus x. But you really can solve for either variable. It doesn't matter. We'll see. Sometimes it's easier to solve for one over the other. So we have x times, now instead of y, what am I going to write in place of y? 24 minus x. And then that equals, we can distribute this. So we have 24x minus x squared. So where is the maximum on this graph? Where the derivative is 0, right? And where the derivative is 0, technically it's only a critical number, and we'll talk about that in general, or in a minute, but we're looking for a max, has to be at one of those critical numbers, a high point or a low point. So we take the derivative. Now we're ready to go. We find the derivative. This gives us what? 24. And this gives us negative 2x. And the max is where the derivative is 0. We find the derivative, that is equal to 0. Okay, and then solve for x. We could add 2x. We get 2x equals 24 divided by 2, and x is 12. All right, so we only came up with one number, so hopefully that's it. And I'm okay if you just go at it, but technically we should remember, because this is really a critical number. So we really should make sure that it's not a false positive. And we really should make sure that it changes from positive to negative to make sure that it is 100% a maximum. Okay, so we'll do that maybe once or twice. Let's at least talk about it here. So 12 is our guide. We want to make sure that it goes from plus to minus. We want to make sure that it goes from increasing to decreasing. Then it is 100% a maximum. So let's see, we could pick, now remember we test it. Where do we test it? We test it in our derivative. Let's write it like this. Derivative of, should we do 0 here and maybe 20 here? It doesn't really matter to pick anything. You could pick 100 if you wanted. All right, so what happens when we plug in 0? This goes away, so we get positive 24. All we care about is that it's positive. And then when we plug in 20, we get negative. So in fact, it is going from increasing to decreasing. So 12 is, in fact, a maximum. So we may phase this out, the checking part, but just kind of keep in mind that we definitely, technically we should. All right, so then just make sure you answer the question. What two numbers? So one is 12. Then most of the time I go back to the original. So x plus y equals 24. If x is 12, what does y have to be? Yeah, and then you just plug 12 in for x, subtract, and y is 12. That one I would not have to check. So 12 plus 12 gives us 24. And what's the biggest the product could be? The 144, right? 12 times 12. All right, should we try another one? Find two positive numbers whose product is 400 and whose sum is a minimum. Kind of the same process. We'll kind of write an equation for like the restriction, so to speak. And then we write an equation that we're trying to maximize or minimize. That'll kind of be the process today and tomorrow. All right, I'll write it. Well, you guys have it. So, all right, so what's our restriction? Product is 400. Product is 400. Number 2. Product. And what does product mean? The answer to multiplication. So x times y. Find two positive numbers. So positive will come into play. I think on one of the homework problems, one of them is negative. So just be aware of that, but then it won't specifically say something about positive. All right. Find two positives whose product is 400. So the product needs to be 400. But whose sum is a minimum. So the sum of x plus y is as small as possible. The sum is as small as possible. So what are we looking for here? We're looking for a minimum. Right? This guy, we're looking for a minimum. But we want it on this equation right here. But where do max and mins come from? Where the derivative is 0. Okay, it comes from those critical numbers. Back to one of the very first days we did, those critical numbers. They truly are critical, right? At least for this chapter. All right, so this was just a little bit harder. Like we solved this for y, we're going to have to divide. 400 over x equals y. And now we got to plug that in. So we've got s equals x plus 400 over x.
You just plug that in y.
Yes, yep. So you solve, right, you're going to take that first equation. You can solve it for either variable. Most of the times I solve for y unless I can really see that there's a benefit for solving for x. Just mainly out of habit more than anything. Okay, so remember, we're going to take the derivative. Critical numbers come from when the derivative is 0, but also where the derivative doesn't exist. However, we haven't found the derivative yet. What number is not in the domain here? If x is 0, it's not even on the graph, right? Because when x is 0, I get undefined and I'm done. So I never, ever have to worry about when x is 0. Okay, so now I'm still going to do s because in order to take the derivative, I'm going to rewrite this. I'm going to rewrite this as 400 x to the negative 1. And now I can actually take the derivative. That's the second derivative. All right, so x goes to 1. And then this, we're going to roll it down, multiply, and then subtract 1. Subtract 1, and we actually get negative 2. Let's write it like this. 1 minus 400 over x squared. You can do either one. But when I write it like that, where would the derivative not exist? It would not exist at 0, but I've already said don't even worry about 0. So my only other option then is where the derivative is 0. Okay? So because there's a fraction, we have to think about where the derivative doesn't exist. If it doesn't exist at 0, and we already excluded that from the domain, we don't have to worry about it. So now we're just back to our old, set it equal to 0. I kind of like leaving it like that. There's different ways to solve this. I would probably just add 400 over x squared because it was negative. So now you have 400 over x squared equals 1, or I can even write it as 1 over 1. And then I like to cross multiply. So x squared times 1, I could write it so you know where that 1 came from, equals 400 times 1. So this guy is this fraction, and then I cross multiply. Don't really need the ones, so if you didn't write them, then you're okay. It helps to put in your notes. And then to solve for x, take the square root. Here is technically where I should do plus or minus. But that's where it's coming back. It says something about find 2 positive numbers, so the negative gets tossed. So our only answer then is 1. And then the only thing we could do is we could check it to make sure in this problem, we could let's at least set it up what it should be. Remember, this side should be negative. It should be decreasing and then increasing for it to be a minimum. Yeah, that's for a minimum. Now just be careful. What's the problem? I'm supposed to be able to pick anything over here. But what happens if I pick 0? Just be careful. Remember, 0 is not in the domain. So in this situation, you cannot pick 0. But But other than that, it's okay. So let's just do 1, and then I don't know, we can do 50, 100, whatever. But if you test those, and remember you test them in the derivative, either one of these, you should get negative and then positive. Okay, so answer is 20, and then it does say two numbers, so I have to go find the other one. I could go right back to here. Rewrite that 400 divided by 20 gives me y. And that actually happens to be 20 as well. Okay, so let's just talk about just real quick, what did we find here? 20 times 20 is going to give us 400. 20 times 20 is going to give us 400. 20 plus 20 gives us 40. Okay? If you choose any other two numbers that multiply to 400, your sum is going to be bigger. Okay? We found the smallest sum possible. If you choose any other two numbers that multiply to 400, when you add them, it will be bigger than 40. Just so that you kind of understand what we're finding. All right, should we try another one? All right, find the dimensions of a rectangle. Okay, now this gets a little bit more, at least a little bit more situational. Find the dimensions of a rectangle with area 1,000 square centimeters, whose perimeter is as small as possible. So, you know, and eventually we could, I think we put like a little situation to this, you know, maybe the vet says like 1,000 square inches, well, this would probably be more than 1,000 square feet, right? This is centimeters, but 1,000 square feet is good for a dog to run around. But I can make that however I want, and maybe I want the perimeter of that rectangle as small as possible because I'm going to put a fence around it, right? And why buy more fencing than I really need? And so something like that. That would be at least one situation where this might come up. And that's kind of what we get into on the back, a little bit more different situations. Okay, so the dimensions of this rectangle, we don't know. So we'll call it X and Y. But what do we know about the area? The area is 1,000. Okay. So area of X times Y. And we know that the area is 1,000. This is almost identical to what we just did. Okay. We want the perimeter to be a minimum. How do you find the perimeter? We know we want this to be a minimum. How do we find the perimeter? Perfect, yeah, right? X plus y, which the best way to write that is 2x plus 2y. Technically, we would do x plus y. But yeah, and you might stagger them. You might say x plus y plus x plus y, but then combine like terms, you get 2x plus 2y. Just be careful there for perimeter. Good. Other than that, now we're ready to go at it. So we're gonna divide both sides by x. 1,000 divided by x equals y. Plug that in. 2x plus 2 times 1,000 over x. So we could make that 2x plus 2,000 over x. No, that's the same thing, right? So what is not in the domain? 0 is not in the domain. Okay, 0 is not in the domain. So 0 comes up at any point. This is still my original. This is now my equation. This is now like my f of x. Okay, this is the guy that I'm working with. 0 is not part of that very original equation. It has no impact or no effect on anything else. All right, so let's still rewrite this though. I'm still going to use the f of x, or I'm just going to do p for perimeter. 2000 x to the negative. All right, and then we're ready to go. Where does these mins and max happen? Where the derivative is 0. So let's first find the derivative. Where is the derivative 0? All right, so that goes to 2, right? Roll this down, so negative 2000, and then x to the negative. And then we want max and min to happen where the derivative doesn't exist, which would actually be 0, but 0 is false because it's not in the domain, or where my derivative is 0. And same thing, it's up to you how you want to solve this. I do kind of like making that back a fraction. 2000 over x squared. But again, because I like to cross multiply, especially when you only have like one fraction on each side, which we can easily create. Add this 2000 over x squared. That way I'm making it positive, which is always nice. And now I really have this fraction, 2000 over x squared, equals this 2, or 2 over 1. Don't think, and not that it's super messy, but I think everything on the homework I can double check. I think, well, let's take a look at the answer and then we'll backtrack. So 2000 times 1 is 2000 equals x squared times 2, 2x squared. Divide both sides by 2. And here's what I'm talking about. How do we get x by itself? We have to take the square root, which there is, 1000 is not a perfect square. I believe everything on the homework is. Okay, so that's kind of nice. I think maybe, I don't know if I added an extra 0. I said next year to take that 0 off. But, does anyone know how to simplify though? We could simplify this to 100 times 10 because the square root of 100 is 10. So this guy, then we can write it as 10, and then this would stay the square root. I think, yeah. Oh. All right, so now we need to find y. Well, that's what it is. Find the dimensions of the rectangle. Okay, so one of the lengths, or one of the sides is 10 root 10. Here's a great place to go find y. I'll just do it in a different color. 1000 over 10 root 10 equals y. We can do a little simplifying there. That answer is not that bad. We could definitely, because there are the zeros, we can cancel that out. A 100 over the square root of 10. And I'm okay if you leave it like that, but this is one time where you do want to rationalize. You want to rationalize if it'll help you simplify. But you don't have to rationalize if it's not going to simplify, but you don't know if it's going to simplify until you rationalize, until you you can kind of look at it and know. So this would be one that if we rationalize, we get 100 square root of 10 over square root of 10 times square root of 10 is regular old 10, and we can cancel those. So y is square root of 10 over 10. So 10 root 10 by 10 root 10. What would that do? That would give us an area of 1,000, but the perimeter would be as small as possible. You're going to go into the fence store and say, I need a length of 10 root 10. But you can round, right? You'd be at least as close probably as possible. And they're not always going to be the same. That's what I was looking at. A lot of times, especially for like the easier ones, that seems to be the case. But tomorrow's will be a little different. And I think 4 is even a little different. So, all right. Or yeah, mine's a little bit different. But all right, so 4 is below. A box with a square base and open top must have a volume of 62,500 cubic centimeters. Find the dimensions of the box that maximize the amount of material used. If you're the box maker, you might actually want the reverse, right? You want as small as possible. But for right now, it's saying, can we max out the material used? So we've got number 3. We've got a box. I'm just going to draw it the old-fashioned way.
Wow.
That work? Where's my architect? Or no. They usually their boxes look so nice. Mine you have to like really like. Wait. All right. Now this helps significantly for us, and so remember we're just doing. Did you draw one? No. The base is a square. That helps very nicely. We have less variables. Okay, the more variables, a little bit more annoying it is. So I'm going to label this X and X because it's a square. Okay. The height, there's nothing about the height. So the height will be different. So the height going up will be different. So how do we find the volume? Length times width times height. The length and width are the same, right? So X times Y. Right? We know the volume is the 62,500. And we can do X times X. We can write that as X squared Y. So because of that X squared, I'd probably solve for Y, except let's take a look at, find the dimensions of the box that, it was minimized. Okay, I'm like, why would it minimize the amount of material used? Does that make sense? If you're a box maker, you'd like it, now again, they might have more requirements on this, but if they just say that's my volume, maybe they're just packing like a powder or something like that, you want your dimensions, or you want your find the box dimensions that minimizes the amount of material used. You don't have to use as much cardboard. All right, so what do we call that? How are we going to determine the amount of material used to make this? That is the surface area. How do you find the surface area? I'll just go A for area. But how do we find the surface area of a box? You have to find the area of every side and add it together. So what's the area of the base? The area of the base is X times X or X squared. Remember, and this is another thing that helps it, there is no top. Okay, there is no top, right? Open top. Okay, so we don't have to take that times 2 because we don't have a top. All right, then we add to it the 4 sides. How do we find the area of one of the sides? That would be X times Y, and we have 4 of them. So we have 4XY. So these are the 4 sides, and this is the base, and we have no top. And we want to minimize this because that's the material used. Now, keep in mind, we're not talking about any excess or anything like that. We're talking the exact amount But it probably correlates, right? Because whatever you have, that excess amount would correlate to each box as well. Now, I kind of like, you know, there's an x squared here and an x squared here. If that was the case, I'd probably solve that for x squared, get rid of that. But I also have a regular x. So I'm just going to go back to my old method, divide by x squared and solve for 1. And then plug that in. We want to minimize this area. Well, let's see, we got a 4, we got an x, and then we got the 62,500 over x squared. Let's clean it up a little. So we've got an x can cancel, and we can multiply the 4 and the 62,000. All right, so that gives us 250, okay, 250,000, but this is a plus. 250,000 over the x is canceled, so we only have 1. All right, so remember, this is my f of x. This is kind of like where I'm starting. What's not in the domain, as usual, kind of. So if 0 ever comes up, we could care less about it because it was not in the original part. All right, so then I want to know where the derivative doesn't exist, unless it's 0, then I don't care about it, or where the derivative is 0. So I'm going to rewrite this one more time because I need this up top. So now I can take the derivative. Derivative, roll it down, subtract 1. Just take your time, roll it down, that makes a negative. And then x to the, make sure you subtract 1. It doesn't go to 0. Make sure you subtract 1. Takes us to -2. If I set that equal to 0, 1,000 over x squared. What was I going to say? Oh, so I kind of did a 2 for 1 here. I said it equal to 0, but I also could just take a look at when this would not exist. It would not exist when x is 0, but we already tossed that, so we're good. So we are okay going back to the setting it equal to 0. I think, and again, there's a lot of different, well, not a lot, but there's definitely different ways to do this. I think I would still do the cross multiply. Especially since this is negative, let's add it to the other side. How are we? I know for a while books, schools were not teaching cross multiplying. You cross multiply, I'll do this 2x over 1. You cross multiply when there's an equal sign in the middle. That's when you get to cross multiply. So this would give us what? 250,000 times 1. And then this one would give us 2x times x squared. Takes us back to it. And now we're going to divide both sides by 2. That's what, 125,000. And then, oh, that makes sense, yeah. How do we undo a cube? Take the cube root. Make sure you take the cube root there. And that gives us 50. So that is the base. The base would be 50 by 50. And then we would just have to go find the height. Did it say find the dimensions? Find the dimensions of the box. Okay, so we found x, which is actually both the length and the width, or the length of each side of the box. And then to find the height, we would go back here to y, so 62,500 over 60 squared. We got 25 for that. Did anyone else? Okay. So, you know, the dimensions would be, I think it was in centimeters, 50 centimeters by 50 centimeters, and then the height of 25. And for web design, it might be easier to state the volume. If we had to state the volume, then we would just multiply that together. That way you don't have to take the 3 in it. I think I put that on the next one. The next one is kind of the reverse. We still have this open box, which makes the problem a little bit easier. Having a square base, those are always nice. For right now, we're not going to go off of that. To be constructed from here, they're saying we have 108 square inches of material. Okay? Probably cardboard, I don't know, maybe metal. What dimensions will produce a box with a maximum volume? So this is the material we have, but we want to maximize the volume. Okay. What dimensions will produce the maximum volume? And then is this right? Did I add this on? What is the maximum volume? All right. So here they're saying this is all you got. This is the material that you're going to use to build the box. Can you maximize the volume? So the exact opposite. All right. So what's our first equation? Let's draw another box. The material to build the box, that is surface area. The material to build the box, that's surface area. Oh, no, sorry. All right, so let's draw our box. That is. So no top. And actually, this should be dotted too. That's fine. And the base is still a square. So this actually, we can redraw it if we want, because those two should be the same. And then the height is still different, or at least potentially different. It could turn out to be the same, but the only thing we know for sure is that the base is the same, because it is a square. But here, the constructed material, that's the surface area. Surface area. So same thing, how do we find the surface area? Remember, no top. So the surface area is the area of every side added together. So the area of the base is x times x, the rectangle, or x squared. And then there is no top, so we don't have to worry about matching it. And then we got the 4 sides going around. Each of the 4 sides going around is x times y. So that's like this front one, but you got a back one. You got this one here is x times y. This is a y as well. And then you got the back. You got x times y, but you have 4 of those. Each side is going to be x times y. Especially or mainly because that base is x by x, which is very nice. Okay, and we know the material, we know the surface area is going to be 108. Okay, and then we want to maximize the volume. So volume is simply length times width times height, length times width times height, which we can write as x squared times y. Same thing. I mean, kind of be nice if you could solve for this x squared, but we'd have x in it, and so that would mess things up. So I think solving for y would probably be the best bet. So this is a little bit messier. So let's subtract x squared. We have 108, actually, 108 minus x squared equals 4xy. And then we're going to divide everything by 4x. So 108 minus x squared over 4x is going to go in for y. So let's take a look. What is that going to look like? Volume, this is what we're trying to maximize, right? All right, so we've got this x squared. Let me put it over 1. And then my y is 108 minus x squared over 4x. Let's okay. Is there anything we can cancel? Might as well cancel if possible. Do we see something that we can cancel? X's, yeah, beautiful, good. This x cancels with at least one of these guys. So we have x times 108 minus x squared over 4. And then again, there's a bunch of different ways to do this. I would probably distribute this x. So we have 108x minus x to the third. And then what I would probably do is I would probably put this over 4 and this over 4. So I have my two separate terms. Most of the time, we would say, hey, you have a common denominator. Let's write this once, and or put this together, and then we just have to write the denominator once. But splitting it up like this gives us our two separate terms that we like. What else? I think 108 divided by 4, that's at least doable, right? That is 27. And if it doesn't go in there, that's okay. I'm going to rewrite this as 1/4 x to the third. All right, so this is like my f of x. Is there any restrictions? Is there anything that would cause that a problem? No, so we do have to think about where the derivative doesn't exist, but let's first take a look at the derivative. So let's take the derivative. So that would go to 27. Beautiful. And then just take your time here, roll this down. So negative 1/4 times 3 is negative 3/4. And then subtract 1 takes us to x squared. And so even though this is kind of messy, it is a polynomial, so we don't have to worry about when the derivative doesn't exist. We don't have anything on the bottom besides a constant, so that's okay. And so even though it looks a little weird, these steps are fairly important to kind of get it to those two terms. So make sure that you follow that. So we can set it equal to 0, and then we're doing the same thing. 27 3/4 x squared. Since this is negative, I'll probably add that 3/4 x squared. I can also put this x squared now back on top. So I have 3x squared over 4 equals 27/7 over 1. So a lot of that extra fraction kind of caused a lot of rearranging. So just kind of follow it through here. And then even here, I moved that x squared back into the numerator. But now we're good. Now let's cross multiply. So 3x squared times 1. And then, let's see, what does that give us? 108. Divide both sides by 3. And that gives us 36. Beautiful, right? And then to undo the square, take the square root. Now, technically, I should do plus or minus, right? Make sure if you're taking a cube root, you do not do plus or minus. I forgot to say that, but for square roots, you should. But X is the length of a box. Can the length of a box be negative? No, that would be an issue, right? So we don't even need to worry about that. And most of the time in real life, you don't need the negative. So it's really just 6. All right, so it would be what? 6 by 6. And then to go find y, it may be a little annoying. Well, we would just work through it. We would do 108 minus 36, and we would do 6 squared over 4 times 6. And I believe that is, but you can use 3. Which would be, yeah, 72 divided by 24. That works. And then, this was all right. What is the maximum value? Okay, so those are the dimensions. And then you would just simply multiply 6 times 6 times 3, and that gives you 108 inches. And depending if they want the dimensions or the volume. Good, okay. So let's do this. So we'll do number 6 tomorrow, and then we just have some harder ones. Okay, I think 6 is the last one, and then tomorrow we'll hit some. The good thing is the harder ones, the same process. Some of the numbers though can be a little iffy, and I don't know how many we'll get to tomorrow, but we'll see how far we get. Okay, so you can do tonight's homework if it kind of matches. Actually, I think 3 is like 6. So maybe skip 3. I wrote like 3. So if you skip 3 on tomorrow's, and then we'll just do it tomorrow. So if you want to try it, that's fine. But otherwise, on tonight's for right now, skip, it would match number 3. And then that'll be the first one that we'll do tomorrow.